Hello everyone. We are learning computer organization and advanced microprocessors, and this is our seventh lecture. In this lecture, we will learn about the digital systems and basic components of circuit designs, like what is the meaning of digital system and what are the different components that we can use to draw a circuit. So let's start. Okay, so now let's start with the digital computer. The term digital computer means we can say that a computer is a digital device, right? And digital means a device, or a digital computer means a computer or a device which works only with the digitals or a digits like 0 and 1, which works under the binary data, which works with the binary data that we call the digital computer, right? And of course, we know that when we give the input to the system in any form, like it can be numbers, it can be character, it can be signals or a command, we can say through mouse with whatever we give, then some images when we scan it. So there are multiple data types, we can say, but when it enters into the system, it gets converted into the signals. So there are in general two types of signals. One is a digital signals and second is a analog signals. And in a present time, most of the computers are digital computers, though some are also analog computers. And normally, an analog computers monitors input signals whose values keep changing continuously. And of course, it deals with physical variables like voltage, pressure, temperature, speed, like that, right? And a digital computer operates on discrete information, that is the digital information, such as numbers, right? And it uses binary number system in which there are only two digits, 0 and 1, and each is called a bit. We know, right? 1 and 0, we call it a bit or a binary digits, we can see. As in the diagram, you can see the graph of the analog signals and the digital signals. You can see that analog signals are continuous in nature, uh, where digital signals has a sudden jump, right? Sometimes you can see a up or a down, up down, up down, so there is a sudden change in the state of the signals. And lastly, in digital computers, we can say that numbers, letters, words and whole text are in a binary form, and that is also known as a machine language. Fine. Okay, so it is about the digital computers. Okay, so now let's see little bit more about the binary information and signals. As you can see on the screen that we have three different images for the same digital signals. The first image says, as you can see over here, in the first image you can see that 1 and 1. So my signal is over here, and when it is 0, if the value is 0, then it goes down this way, right? So that's why we call it a sudden jump. What we call it a sudden jump. Again, when there is a 0, and again when the value comes 1, there is again sudden jump and it goes upwards. Again there's some state, sometime for the state is a 1 1, again the value comes 0 and then it comes down. So we can say that there is a sudden jump, what we call a sudden jump. So that's why we say that analog signals are continuous in nature while digital signals has a sudden jump. Now let's see the second image. In a second image, there are few things that we need to learn. That is, if there is a 1, if the value is 1, that means it is on. We call it on, and there is a high voltage of a 5 volts. There is a high voltage and the value of the volts is 5. And same and for the 0, 0 means there is a off state and low and a 0 volt. So power supply is a low, high voltage is a high, and here we have voltage low, but here we have a 0 volt and here we have a 5 volts. Fine. So whenever there is a 1 means it's on, there is a value, there is a data, and the voltage is high. And how much voltage we required for that? 5 volts we required. And whenever there is a zero, means there is off, there is no data, there is a low voltage, and there is a 0 volts applied to it. So that is about the voltage and on off condition. And the final we have a small brief image, we can say, which indicates that whenever it's up, whenever it's upside, there is always a 1, and there is a downside, that is always a off. And on means here I have 1, here I have 1, here I have 1, and here I have zeros. Okay, so clear everyone? So let's go to the next slide. Okay guys, so now you have to perform two activities. First activity is to identify the input. Here we have signals, here we have a graph of the signal, and from that you have to identify that what input was given to the system. So just identify the input from the graph. And the next activity is you have to draw signal graph from the given input. Here we have given the capital A as an input. So now just draw a graph that what would be my digital graph or a signal graph. Fine. Okay. Okay, so now let's see the most important topic, that is logic gates. So very first, in this slide we will see about the symbols, expressions, and the truth table. But before that, what is logic gate? So a logic gate is an elementary building block of a digital circuit. We can say that if you want to design a digital circuit, then you need a logic gate. So that's why it's an elementary building block. And most logic gates have two inputs and one output normally. Of course it can have multiple, but we'll see it later on. So normally any gate has two inputs and one output, and at any given moment every terminal is in one of the two binary conditions that we know, right? That low or a high. Low means a 0 and a high means a 1, and represented by the different voltage levels. So we know that 0, that is low level, means there is a 0 volt, and if it's a high, that is 1 condition, means there is a 5 volt. So the logic state of a terminal can and generally does, we can say, change often as the circuit processes data, we can say. And in most logic gates the low state is approximately 0 volt, while the high state is approximately 5 volts, that is the plus 5 V. Fine. There are basically 7 logic gates. There are, here in the diagram you can see 6, but there are total 7 logic gates. One is a on. First is AND gate, then OR gate, NOT, NAND, NOR, XOR, and last we have not mentioned over here, that is the XNOR gate, that you can learn after learning all these gates. We'll see it one by one. So very first, let's start with the AND gate. As you can see in the diagram, AND gate basically a gate which can have 2 or more inputs, and its output is always is true if all inputs are true. You have to keep in mind this thing. As you can see that the value of the output 1 is only true when all the values are 1. So that we call the AND gate. Here it's a logical, here is a graphical presentation or a graphical symbol for the AND gate. Here we have algebraic functions, that is, if F is my output, then my equation is A dot B, or simply AB, and from this we have this truth table, right? Okay, so I assume over here that you know about the truth table. And similar way, we have OR, NOT, NAND, NOR and XOR gate. And here we have all the symbols, and here we have all the algebraic functions which you need to remember. And here we have the truth tables for all the functions or for the algebraic functions. OR gate symbol is like this. NOT has a triangle, we can say, and there is a one small circle. Now let's see about the NAND gate. So NAND gate, as you can see that there is a, here we can say an AND, that is not AND. See, I have AND gate, right? And what if I want inverse of NAND gate? That is not AND. If AND and inverse of AND is a not AND. So simply put a small circle over here, just like see this, right? AND gate is there, and then I have a small circle which creates NAND gate. Same with the NOR gate, right? So what about the XOR gate? Here the meaning of the X is exclusive. What is the meaning of that? That is exclusive OR. So as you can see that I have OR gate, but to make it exclusive we have this arc, and then we can get exclusive gate or exclusive OR gate, we can see. Mind the function, it is little bit different from others. Like for AND we have a plus dot sign, for OR we have a plus sign, for NOT we have bar sign, for NAND we have again the A dot B bar, then for NOR we have a plus B bar, but for exclusive OR we have a circle and plus sign, and a plus sign we have. Fine. Okay, so this is about the gates, their symbols, their algebraic functions, and truth table. Before we go to the next slide, let's see once about the truth tables. So let's see, for AND we know that if my both the values are true, means this both the input should be true, then and only then I'll get 1. Or means what? Either this or this. So I can see that this or this I'll get 1. But even if I have all the values true, then also I'll get the output. For here I have one true values. For NOT, it's inverse case. If it's a 0, output would be 1, and if it's a 1, output would be 0. It's an inverse value. Okay, now say this. As we know that NAND gate is an inverse of AND. It means what? See the truth table. See this. From AND to NAND. The NAND truth table is completely inverse of the AND truth table, and similar way the OR truth table, see this truth table, NOR truth table is completely inverse of the OR truth table. And exclusive OR means the minimum value should be true. Exclusively this one value should be true, then we can say that it's an exclusive or exclusive OR gate, we can say, and then only we can get the true value for that. I hope that all these concepts are clear, because this is very important slide, because all these expressions and the symbols and truth table we need to apply when we will draw the circuits. Okay. Okay, so now let's start that how to draw a digital circuit from the Boolean expression, or how to draw a logic diagram from the Boolean expression. As you can see on the screen that here we have total 4 expressions and 4 logic diagrams. First, second, third and the fourth. So here we'll learn that how to draw this diagram from these expressions, right? Okay, so here I have an expression a plus b dot c, and here I have the logic diagram or a circuit diagram. After I'll show you or I'll teach you that how to draw this, after that you have to do by your own, you have to draw the logic diagram by your own for 2, 3 and 4. So I'll teach you, I'll show you how to draw in for the first, and rest of the 3 it will be your activity. Okay, fine. So let's start how to draw the logic circuit or a digital circuit from the Boolean expression. So here we have a Boolean expression, that is A plus B. So what is our expression? Our expression is A plus B and dot C. This is our expression. Now very first, identify the variables or a total input lines from the given expression. So here we have total 3 variables. Here we have total 3 variables. 1, 2 and 3. 3 different variables we have. From the given variables, we have to decide our input lines. So let's draw the input lines first. A, B, C. So just draw this way. A, B and C. Fine. Okay. Now draw the input lines. Simply draw the lines. Okay. So here we have 3 inputs, that is 3 variables and 3 input lines A, B and C. After that, identify the expression or the relationship between 2 variables, or what is the gate we are going to apply on the 2 variables. So here as we can see that A plus B. Here we have A plus B. As we can see that A plus B. Here we have an expression. Plus sign we use to, plus sign indicates the OR gate, right? So start with the A, draw the line, then take the B, then okay. So now I have A and B. What is the relationship between A and B? That is OR gate. Okay, so simply draw the OR gate. Perfect. So this is my A plus B. So what I got as an output? I got A plus B. This is my A plus B output. I have inputted A and B and I got A plus B as my output. Now the term, now the time to draw C. Fine. So what is the relationship between these two? That is dot operator. So A plus B dot C. We got the A plus B. Now the time to add C. Now let's take C. Okay. So here I have C. And what is the relationship between these two? So C, and here I have B. Right. Okay. And here we will draw which gate? Because here we have dot operator. So dot means which gate? Dot means we have AND gate. Okay, so just draw AND gate. And at the end we will get A plus B dot C. Simple. Clear? So this is about how to draw the digital circuit from the given expression. Okay, so here also you have an activity to draw the digital circuits. Here you have expressions and digital circuits given. So just practice it and make it sure that you don't skip it. Fine. Okay. Few more designs you have to draw, and also check that you are going right or not. Okay, so that's it for today. Keep learning. Happy learning. Thank you.